Hi AP Calc students, this is video 4-5 to be watched Tuesday 12/6 actually. And we're on page 11 in the green packet. So this is the notes packet. The homework that corresponds to this is page 10, number 1. I'm going to shorten this lesson significantly. We're not even going to do the front page. It's a nice exercise, but I could save it for some other time if I want to do it. And so let's just flip to the back. All right, so I'm just going to lay out some information in these first two boxes, and then we're going to do one example. So what I'd like you to do is please, this is where we're going to write Susan's table. I told you about her. I met her over the summer. She's a AP Calc teacher down near Pittsburgh, and she has her students whenever they're doing problems that have to do with derivative graphs or determining certain intervals on an original function using the derivative or stuff like that. She has them write down this table. So I'm going to call it Susan's table, and so it has 3 columns, F, F prime, F double prime, and each row of the columns is going to give us like equivalent things, okay? So first, if F is increasing, that means that F prime is positive. Okay, so these two things, F increasing is the same thing as F prime positive. They imply each other. And then decreasing negative. And then you will know that you have an extrema, like a max or a min, a local max or a local min, if F prime has a sign change. Okay, if it changes from positive to negative at that point, at that critical number, then it would represent an extrema of some kind. F will be concave up if F prime is increasing, and now we get into the F double prime column. Before we couldn't really say much about F double prime given these things, but now if F is concave up, that means that F prime is increasing. Well, guys, F double prime is just the derivative of F. So if you look back up here, if a function's increasing, its derivative is positive. So same thing down here, because this is just the derivative of that. So if a function's increasing, if F prime is increasing, its derivative F double prime is positive. Okay? So we're sort of just repeating this down here. Concave down, F will be concave down if F prime is decreasing over time, and then same thing, if a function's decreasing, its derivative is negative. And then a point of inflection where we change from concave up to concave down, that will be, you will know you're dealing with a point of inflection if you've got an extrema of the derivative, of the first derivative, and you'll know you have an extrema of the first derivative if you observe a sign change in its derivative. Okay, its second derivative. So this we're like sort of repeating down here. Okay, so guys, these second derivative theorems, so we've actually already been using these first 3 things with the first derivative test, but today we're going to determine intervals where a function's concave up, concave down, and we're going to determine inflection points. So we're going to be dealing with these last 3 rows. Okay, and then here I grabbed these off of a website right down here. So they're just basically another way of saying some things we said over in the chart, but this is called the inflection point theorem. If F prime of C exists and F double prime of C changes sign at x equals C, then the point C comma F of C is an inflection point of the graph of F. And if F double prime of C exists at the inflection point, then F double prime of C equals 0. Okay. All right, so there's that. And then the concavity theorem, if the function f is twice differentiable at x equals c, then the graph of f is concave upward at c comma f of c, if f double prime of c is greater than 0 is positive. Okay, so what they're saying right here, concave up if f double prime is positive, that's right here. Concave up f double prime positive. And then concave, basically the rest of the theorem says concave down negative. Okay, and then down here we would have basically the inflection point theorem right there. Okay, so here's an example. And we're going to explain all. Okay, every time we do these things, we're going to be explaining them. So part A, determine all inflection points for the function below. If you are determining inflection points, you need to be using the second derivative, okay? So if you look up here, a point of inflection is going to occur where there's a sign change on the second derivative. So when we were determining extrema, we were looking for a sign change on the first derivative. Now we're looking for a sign change on the second derivative. So we've got to get the second derivative. Okay, and speed this up, guys, if you would like to. I don't have to write that again. So I'll just go f prime of x. I got to find the first derivative in order to get to the second derivative. So 3x squared minus 6x plus 1. That's the first derivative. Okay, now I'm going to take its derivative. So the second derivative is 6x minus 6. Okay? So just like with the first derivative number line, you're going to split the second derivative number line up wherever at the critical numbers, wherever the second derivative is 0 or undefined. Okay, so we've got the critical numbers, 6x minus 6 equals 0. So x equals 1 is where we're going to split that up. All right, so now I will do a number line test. I've only got one critical number, so there's 1. And how did I get this critical number? It was because f double prime was 0. And then I'm going to look, I'm going to do testing points to the left and right and see if I observe a sign change. So to the left of 1 is 0. I'll use that, so we get negative on that side. And to the right of 1, like I could pick 2 and I would get positive. I'm plugging, oh, this is the f, I should go like that. This is the f double prime number line, all right? So, okay, all inflection points for the function, so I would have an inflection point here. Let me see if f prime of c exists. All right, so since I've got a sign change at this x value, then this is going to be my point of inflection. So for part A, I know that the x-coordinate is going to be 1, but I've got to find, and the inflection point is on the original function, guys, so I'm going to go f of 1. I get 1 minus 3 is negative 2, plus 1 is negative 1, minus 2 is negative 3. I'm exhausted. Yes. Okay, so there's that. So I'm going to say point of inflection is 1, negative 3. And remember, please explain, because oh, guys, I guess, I'm looking at this inflection point theorem, and so I guess we got to make sure that f prime of c exists. Okay, maybe, yeah, I'm just noticing that. And of course it does. I mean, there's no undefined values. These are all polynomials, but okay, I just caught that. I'm not really sure why we need to do that, but okay, so the point of inflection is there, and then I'll just say because f double prime changes, you could say changes sign, I'll be a little more specific, changes from negative to positive at x equals 1. Okay, so that was part A. Now part B. Okay, so we were looking for, so point of inflection, we were looking for a sign change on f double prime. Now for part B, determine the intervals over which the function is concave up. Well, we know f is going to be concave up if f double prime is positive. Okay, so on the positive interval, it's concave up. On the negative interval, it's concave down, the original function, because its second derivative is positive and the negative. So for part B, I'll say f is concave up on 1 to infinity, and then I'll say because f double prime is greater than 0 on this interval. And then for the concave down part, guys, just basically say the reverse of that. So for part C, f is concave down on negative infinity to 1 because f double prime is less than 0 on this interval. Okay, so that wasn't too long of a video. There's the example, and don't forget to do the practice problem, which is on page 10, and it's number 1. And we will have a quiz on this tomorrow. Okay, guys, I'll see you soon. Bye-bye.